welcome to the Simons Institute for the Theory of Computing. I'm Alex.
Well, welcome to the Simons Institute and this program on quantum Hamiltonian complexity. So I thought I'd start off by providing some kind of an introduction to the field of quantum Hamiltonian complexity, because it's rather new, and even the people who are working in it work on one part or another of it, and so it's always good to have a reminder, and of course hopefully some of you are also new to the field and would just like to learn about it. So let's just make sure. Sorry, I seem to have a problem here let me just see if it's the, oh yeah, it was the, I just need, thanks. Okay, so sorry. So let me start from the basics, which is where we start from in quantum computing, which is this remarkable fact about quantum systems, which is that the state of an n-qubit system is it requires 2 to the n parameters to describe, rather than order n, which is the case for a classical system. So if it's an n-qubit system, the state is a superposition over all possible 2 to the n n-bit strings, each with its private amplitude alpha sub x, which is a complex number. So another way that we usually think about it is, of course, that the state is a unit vector in a 2 to the n dimensional complex vector space, the Hilbert space. Okay, so that's of course the starting point of quantum computation. The other starting point of quantum computation is the fact that nature guards these resources extremely closely by making sure that when you actually try to access the quantum state, you only see n bits of information. So you actually see x with probability alpha x magnitude squared. And so this exponential superposition is sort of hidden behind the scenes. And so, this is, of course, the basis of quantum computation, both the possibilities and also the frustration of it. The possibilities because there's this exponential amount of resources, the frustration because you cannot really get at it until you work really hard. Okay, so now the main question in quantum computation is, what do these exponential resources, combined with this limited access, tell us about computation, and what can we compute with it? And there's the flip side of this coin, which is, what does it tell us about physics? The fact that you have this very strange description of exponential power and limited access. Surely this has a lot to say about what's possible and what's not possible in physics. And of course, this goes back to the very foundation of the field of quantum computation. I mean, these were questions that we really did think about and talk about back then. But back then, there were a few missing pieces. So first, we didn't understand quantum computation that well. We didn't have many techniques around. And then a lot of things happened since then. So the field of condensed matter moved forward and started thinking about highly entangled states and topological order, possibly somewhat influenced by ideas in quantum information and quantum computation itself. And then, of course, technology moved forward a lot to the point where people have been implementing rudimentary quantum devices, and so questions about those have arisen. And of course, there are new techniques in quantum information and quantum computation. And this has led to the birth of this new area called quantum Hamiltonian complexity, which where there are interesting things to say about the implications of these basic properties of quantum mechanics for for physical systems themselves. So let me try to outline some of these basic questions. So one direction you can go with all this is you can say, well, if quantum states have this exponentially large description, how is it possible to do physics at all? I mean, how can we, mere classical beings with polynomial computing power, with limited amount of information processing power, how can we possibly comprehend? Oops, sorry. How could we possibly comprehend, the possible states of quantum systems and much less understand their properties? And so one possibility is that, in fact, this exponential description, maybe in order to get quantum states which have this exponential description, you actually have to engineer them, and because obviously engineering quantum computers has proved to be a very challenging task. So you could maybe imagine that there are natural classes of quantum systems for which you can actually describe them very succinctly classically, and you can understand them well classically. Surely that must be the case, because after all, physicists do study quantum systems, and to study them you've got to have a classical description of them. And so that's the first theme. So are there natural classes of quantum states which can be described very succinctly and worked with much more, which we as classical beings can actually work with? So another way of sort of imagining this, thinking about this question is, well, you have this exponentially large Hilbert space, right? It's an exponential dimensional Hilbert space. So could it be that there's a small corner of it where many natural quantum states sit, and inside, and this small corner is sort of easily described classically. So this is the corner that we can understand as mere classical beings. Okay, so that's one theme. The second theme, as I said, had to do with testing quantum systems. So again, here the issue is that, as we saw, quantum systems, they have exponential power, exponential descriptions, but on the other hand, we have limited access to it as classical beings. So now, imagine what this means for, what happens when you actually implement a quantum system, and now say that you don't, for various reasons, you don't entirely trust this quantum system. So you might not trust it because, well, maybe it's being used in quantum cryptography, so cryptography and trust don't go together. Or maybe you don't trust it just because, well, whenever you build some device, you really do need to test it. So how would you, how do you test something which is exponentially more powerful than you are? So one way we can think of this whole issue of testing quantum devices is, well, let's get it down to the basics. So there's, let's think of it as a black box where, since we must interact with it as classical beings, let's imagine that the input and output are digital, and let's make them binary, just without loss of generality. And let's say that, just to underline this fact, the input is in the form of one of two buttons labeled 0 and 1, and the output is in terms of one of two lights, each labeled 0 and 1. And so that's how we communicate with the device, which might be exponentially powerful, which is supposed to be performing some functionality. And so how do we actually verify that it does have that functionality, or it's internal to this device? What's going on is what we expect. Okay. So now you might be thinking, where on the earth do you get a black box in real life? Well, there are companies that do sell black boxes, and we do want to test what's inside, or that they do behave according to claims. Okay, so now this theme of untrusted quantum devices, as I said, comes up in many, many contexts, in cryptography, in actually in this field called certifiable random number generation. So this notion that you can use quantum mechanics to generate true randomness. But now if you want to actually test, how do you certify that the output is actually random? In testing whether a claimed quantum computer is truly quantum, like with a D-wave machine, and even in testing quantum mechanics itself. So I'll say a little more about this as we go along. Okay, so now what I plan to do in this talk is talk about these two themes and to underline what are the interesting features from our viewpoint about this, and why this was an area to that precipitated this actual special semester here at the Simons Institute. So okay, so let's start by talking about this whole notion of the description complexity of quantum states. So do natural quantum states somehow exhibit exponential complexity, or could they be described more succinctly? Okay, so the kinds of quantum states we'll focus on are ground states of local Hamiltonians. So this is one way to specify a physical system by specifying the Hamiltonian or the energy operator. So let's say we have a lattice of particles. Let's say each of them could be it's a two-level system or qubit, or it could be a d-level system or qubit. And we have interactions between these particles represented by terms of this Hamiltonian. So each term of the Hamiltonian describes the interaction between neighboring particles. And now what we'd like to understand is what does the ground state, the lowest energy state of this system look like? So this is sort of the central problem in condensed matter physics, to understand low energy states or ground states of local Hamiltonians, because properties of this ground state determine the properties of materials. So what we'd like to know is, does this ground state necessarily have a polynomial description? And if not, then can we somehow restrict the class of Hamiltonians to some natural, fairly general but natural class where we can get this polynomial description? Now, there's a trivial answer to this. The trivial answer is that each of these terms of the Hamiltonian is sort of local, and it has a constant size description. And the number of terms in the Hamiltonian is polynomially bounded. So of course you can describe the Hamiltonian, and then say if the ground state is unique, you can sort of say it has a polynomial description, because you just say, I mean the unique ground state of this Hamiltonian. Okay, so it's a very precise answer, and it's as useless as it's precise. So the actual question that you want to solve is we want a polynomial description that allows you to compute interesting quantities efficiently. So what are these interesting quantities? You want to compute the ground state energy and 2-point correlations, or any local observables, any observables involving small numbers of particles. And so, in some sense, one way you can describe quantum Hamiltonian complexity is it's an area, or at least a good part of it, fraction of it, lies at this intersection of condensed matter physics and quantum complexity theory. So now there's a very basic reason why quantum Hamiltonian complexity lies at this intersection, and this basic reason has to do with a correspondence between the basic problems in the two fields. So in condensed matter physics, the basic problem is you're given a local Hamiltonian and you want to understand its ground state. In complexity theory, the basic problem is you're given a constraint satisfaction problem, like satisfiability, and you want to understand if there's a satisfying assignment or if there's a solution, what's the best solution to this constraint satisfaction problem. And it turns out that these two problems are very closely related. In fact, the local Hamiltonian problem is a generalization of the constraint satisfaction problems. It's a quantum, this is the quantum generalization of that, or that's the classical restriction of the local Hamiltonian problem. Okay? And so once you realize this, you actually realize that there's a dictionary that allows you to translate between these two settings, because the energy of a state corresponds to the number of unsatisfied clauses of an assignment here. Okay, so states here correspond to assignments, energy corresponds to the number of unsatisfied clauses, ground state corresponds to the solution to this constraint satisfaction problem. But of course, even though there's this dictionary, the actual motivations are quite different. On this side, you study these problems because you want to understand these properties of ground states and therefore the properties of materials. Here you want to study these constraint satisfaction problems to understand, because these are interesting computational problems, and we like to do combinatorial optimization on them. Okay, so now let me just try to describe this local Hamiltonian problem a little bit more closely. So each term of this Hamiltonian, so imagine that each term involved maybe not just nearest neighbors, but let's say it was k local. So here I've drawn a 2 local Hamiltonian because you have 2 particles interacting with each other. But you could have a k local Hamiltonian where you had k particles interacting with each other. And then if these particles were qubits, so if they were 2 level, then your each term of your Hamiltonian would be a 2 to the k by 2 to the k Hermitian matrix, describing the interactions among these k particles. Now, the way we think of the Hamiltonian is that it assigns an energy penalty to the state psi. The total energy is the sum of the energy penalties assigned by each term, and the ground state is the minimum energy state, or the eigenvector. So when we write out, just to, I'm sorry, this is probably, just to make sure that everybody's on the same page. The Hamiltonian would now be, if there are n particles, it would be a 2 to the n by 2 to the n Hermitian matrix. Each of these terms, h sub I, is tensored with the identity, and then you add them up. And so the entire complexity of the local Hamiltonian comes from the fact that these terms of the Hamiltonian don't commute with each other. And so when you're looking for the ground state of this Hamiltonian, you're looking for something you're looking for the minimum eigenvector of this Hermitian matrix, which of course is the sum of these terms which don't commute with each other. Now, let me just spell this out a little more in detail, just to make the correspondence more clear for the computer scientists, and maybe also for the physicists here. So if you look at the constraint satisfaction problem 3 satisfiability, so that's there you're given a Boolean formula on n variables, x1 through xn, which is a conjunction of clauses, C1 and C2 and Cm. So you have m constraints, each of which consists of a clause which is a disjunction of 3 literals. So you might have a clause such as x1 or x2 or x3. And now, okay, so why is this a special case of the local Hamiltonian problem? So this would be a 3 local Hamiltonian problem. So the n bits correspond to, there are special cases of n qubits. A clause, x1 or x2 or x3, corresponds to a term of the Hamiltonian, which is diagonal. So now everything's going to be diagonal in the computational basis. And the only assignment which is going to be assigned a penalty is the one that doesn't satisfy this clause, which is x1 equal to x2 equal to x3 equal to 0. And so this term of the Hamiltonian would look like that. It would assign an energy penalty of 1 to, if you had the all zeros assignment, to these three variables, and 0 otherwise. And so now, of course, what you would do is tensor this up with the identity on all the other bits, and then you add this up over all the clauses, and that's your Hamiltonian for this problem. But of course, since we are, since all terms of the Hamiltonian are diagonal in the computational basis, we know that all truth assignments are going to be eigenvectors. So eigenvectors are going to correspond to just n-bit strings, and each such eigenvector will have eigenvalue, which is going to be the number of unsatisfied clauses. And so the satisfying assignment would be an eigenvector with eigenvalue 0. Okay, so that's the correspondence between satisfiability and local Hamiltonians. Now, as I said before, there's this dictionary in translating local Hamiltonians to constraint satisfaction problems. So the next part of the dictionary lies in realizing that the Cook-Levin theorem, which says that satisfiability is NP-complete, it has a corresponding theorem on this side, which was discovered by Alexei Kitaev, who showed that approximating the ground energy of a local Hamiltonian is QMA complete. So it's complete for the corresponding complexity class quantum Merlin-Arthur. And for our purposes, what this means is that there's no sub-exponential size classical witness for QMA complete problems. What does this mean? So what it says is, if I give you a local Hamiltonian, and I ask you, could you tell me figure out what the energy of this, the ground energy of this local Hamiltonian is? This is a pretty hard problem. But in fact, this QMA completeness is telling us that it's hard in an even more extreme sense. It's so hard that even if somebody were to solve the problem for you, okay, even if there was an untrusted party who actually knew the answer to the problem, and they were willing to help you, but you don't trust them, right? Then there's nothing short of if they were to say something to you which is short of an exponential amount of information, then there's nothing you can do with it, right? Then it's completely then that information would just be completely unconvincing. Okay, so the point is that if you're given a classical satisfiability problem, and even though satisfiability is hard, we don't know any sub-exponential time algorithm. If somebody were to solve the problem and say, I know a satisfying assignment, they could just hand it to you, and this would be n bits of information, which would be completely convincing. For this QMA complete problem of local Hamiltonians, where you're trying to approximate the ground state energy, the claim is that there is no such short classical description that's going to convince us, right? If there's somebody who knows the answer but you don't trust them, there's nothing they can say which is short of exponential size that would be convincing. Okay, so
it's more than just witness.
A witness for whatever the energy is, right? So there's no effective short description of the state which allows you to do even simple tasks. Okay, so now so far what I've pointed out is that there's this very that there's this very basic connection between these central problems in condensed matter physics and in quantum complexity theory. Now, the other reason to study this correspondence is that there are very beautiful questions that arise here. And some of these questions are open questions, and some of them we have, there's a lot of progress in so far. So let me describe some of these questions and some of the progress that has been made. So, one of the crown jewels in complexity theory is the PCP theorem, which says that not only is NP is satisfiability NP complete, but it's also NP hard to even approximate the minimum number of unsatisfied clauses. So it's very hard to tell, given a 3-sat formula, whether it's completely satisfiable or whether there are no more than, let's say, 7/8 of the clauses are 7/8 plus epsilon fraction of the clauses are satisfied. So this was a really remarkable theorem. We could ask, is there a quantum analog of it? And it turns out, people have been trying for some time, but we don't really know what the answer to this question is. And so the interesting thing is, this is one of the rare cases in complexity theory where we have a question whose not only do we not know the answer, but we don't even know which way to actually guess. So people, who've been looking at this question have guess in different directions whether one should have a quantum version of the PCP theorem or not. Now, if there was such a quantum version of the PCP theorem, then we'd have actually quite an interesting interpretation, which very, very loosely you could sort of say, this is sort of asking the question, can quantum systems exhibit this kind of exponential complexity even at high temperature, even at room temperature? Okay, so as I said, it's sort of a very rough connection, but let me sort of say that. So let's say that you had a quantum system at room temperature. So now it's in a Gibbs distribution, right? So now the claim is, if you could sample from this Gibbs distribution. So if you can sample from this Gibbs distribution, then you would be getting a relatively low energy state. Okay. So in other words, if there's a quantum PCP theorem, okay, so already we understand that there are quantum systems for which it's QMA hard to approximate the ground energy. But now, if there's a quantum PCP theorem, it says, given this question of approximating the ground energy, you can translate it into the following kind of question. So we are going to take this Hamiltonian and we are going to massage it into a new Hamiltonian, and it's going to have the property that if the ground energy of this original Hamiltonian was low, then the new Hamiltonian is going to have very low ground energy. But if the ground energy in the old Hamiltonian, the original Hamiltonian was a little bit higher, then here the ground energy is going to be extremely high. So now you massage the Hamiltonian, you prepare the system, and you sample from the Gibbs distribution, and now you check to see now you have this gap, right? So you're either in case 1, ground energy is this low, case 2, ground energy is this high, and you check to see what kind of you sample a few times from the Gibbs distribution. And if you ever see a sample whose energy is lower than this one, then you know that you're in this low case. So you've made a distinction between this energy and that one.
So does that apply to any polynomial time transformation, like effective?
Yeah.
But it's not clear that's all implementable as a physical. Like you use, I don't know, finite field arithmetic to make it a PCP theorem.
It's as long as you have a polynomial time transformation.
Polynomial time is enough. I mean, implementability. I see. Okay.
Polynomial time we think of as. Yeah. Okay, so okay, so let's go back and so far we talked about the hardness of finding quantum states. So the QMA completeness really showed us that in general ground states of quantum of Hamiltonians are very hard. Even approximating the ground energy can be a very hard task. But let's go back to this question: are there natural classes of quantum states for which there's a polynomial description? So it's obvious that if we are going to be looking at ground states of local Hamiltonians, we have to restrict them further. And so why do we believe that it should be possible to do so? Well, here's one reason. It's because actually physicists have been doing this for some time, for some special systems. So in particular, there's this heuristic called DMRG from about 20 years ago, which has been extremely successful in computing ground states and low energy states of one-dimensional quantum systems on a line with nearest neighbor interactions. Okay, so what this heuristic does is it actually computes an approximation to the ground state, and it represents it in a particular kind of format called a matrix product state, which is a special case of a kind of tensor network, which we'll hear about in this workshop. And so there's this succinct, polynomial-sized description of the quantum state from which you can actually compute local observables, energy, correlations, etc. Okay, so now, how can we understand the success of this algorithm, and how do we actually try to understand what kinds of Hamiltonians we should be able to solve? So it turns out that the way to understand this question is to understand something about entanglement. So the main obstacle to describing quantum states succinctly is quantum entanglement. So if you take your quantum system and you divide it into two parts, A and B, then entanglement is the quantum analog of correlations between the two sides. So if you think of the quantum state, it's a superposition over all the classical configurations. The probabilistic analog of that is a probability distribution over all the n-bit strings. And then entanglement between A and B is really the quantum analog of correlations between the left side and the right side in the probability distribution. So it turns out you can actually quantify the amount of entanglement between the left and the right side of the system. And the way you quantify it is by saying, if you measure this left side of the system, then the number of bits of entropy you get in the distribution, that's a measure of the entanglement between A and B. Now, of course, the number of bits of entropy you get depends upon which measurement you perform. And so you must perform that measurement which gives you the minimum possible amount of entropy. Right? So you choose a basis in which to measure the system, and you choose that basis in which you get the minimum possible entropy when you do the measurement. So and that's a concrete measure of how entangled the two sides of the system are. Okay? So what matters for the purposes of what I'm saying is that there's some precise measure of entanglement that we can put. And okay, so now it turns out that there's a really beautiful and sweeping conjecture about how entangled ground states of local Hamiltonians are. Okay, so and it's it's almost completely general. So it requires one condition here, which is that your local Hamiltonian has to be gapped. So what does gap mean? So gap means that the ground state energy and the energy of the first excited state, they must differ by a non-negligible amount. So this is like the quantum analog of satisfiability, where if you have a satisfying assignment and then the next possible not satisfying assignment is going to violate at least one clause, right? So the gap here would be 1, and so gap local Hamiltonians are the quantum analog where the gap is at least some constant, not necessarily 1, it could be 0.5 or 0.01, but it has to be bounded by a constant. So now for these gap local Hamiltonians, the claim is that the ground state is not very entangled, and the way that's formulated is by saying that if you were to take the system and partition it into 2 parts arbitrarily, so you partition the particles into those inside this volume and those outside, then the claim is that as far as the ground state is concerned, the entanglement between the inside and the outside grows proportional to the area of this boundary rather than the volume, which is the number of particles inside this part of the partition. So this is actually this is a long-standing conjecture in condensed matter physics. It somehow it had its origins in the holographic principle in cosmology, but it was really precisely formulated only about a decade ago using ideas from quantum information. But the important thing to remember here is, of course, a law is a conjecture, right? So even though this is a beautiful sweeping conjecture, and so by the way, I should say one other thing about this conjecture. So even though precisely stated, it's only talking about the entropy scaling like the surface area. Morally, it says more. Morally, what it talks about, it's really saying is that the entanglement really sits close to the boundary. It's local, and so if that is the case, then you should expect to get a succinct classical description where you describe the quantum state by describing the entanglement at the boundary, and then once you describe the entanglement, you're free to describe the quantum state inside and outside sort of separately. And so there are these beautiful structures called tensor networks, which Zeph will actually speak about on Saturday morning, which actually give you a precise way of doing this decomposition and actually describing states succinctly. Okay, so now what do we know? Yes?
Can you explain just a little bit more the connection to black hole entropy? Because I think that the black hole entropy stuff is supposed to come from systems which are fundamentally non-local, right?
Yeah, so I'm way out of my depth there, but maybe Patrick would be the. Actually, I should just skip this, but unless you want to add a.
I think there's a long story to tell.
That's probably a good answer.
Umesh,
Yes.
how does it not contradict to QMA hardness? So if you have a concise description of the solution,
Yeah.
then how can it still be QMA hardness?
Right. So Mario's question is how come why does this area law not contradict QMA hardness? And the answer is this gap condition. So it turns out that the QMA hard instances have a gap, a spectral gap, which scales inverse polynomially in n, in the number of particles. And so but this is a so this is a special class of Hamiltonians. But it's a very interesting class of, it's a pretty general class of Hamiltonians. And so it's a way of distinguishing and saying, well, look, if you're going to be completely general about it, you get QMA hardness, but maybe there's a very large class where you don't get it. And here's a very principled reason why you might be able to avoid this kind of hardness. Yeah.
But on similar lines, this intuition you gave earlier about the complexity at higher temperatures and so on, where does m versus m square relate to that? The gap of m versus m square. In the search for the quantum PCP theorem that it implies potentially.
It's a different kind of gap.
Oh, so let me try to actually let me try to address this. Let me say something that's clarifying, and then hopefully it addresses what you're saying, and if not, okay. So let me just talk about the scaling of these gaps, right? So let's say m is the number of constraints or the number of terms of the Hamiltonian. Now, when we say a gapped Hamiltonian, so what are we saying? We're saying the spectrum of the Hamiltonian goes from, let's say, 0 to m. Okay, because let's say that each term of the Hamiltonian has norm 1, so the maximum energy can be m, and let's say it's frustration free, so the minimum energy is 0. Now, saying that it's a gapped Hamiltonian means that the gap is a constant, so maybe 0.1, right? So the energy ranges from 0 to m, and say the ground state has energy 0, and the first excited state has energy 0.1 or something. Now, what would it mean to say that there's a quantum PCP theorem? To say that there's a quantum PCP theorem would mean that what we'd be saying is we can approximate the ground energy to within an additive factor of one, within 1 over polynomial in m, right? And that's what we are trying to do. That's the task that we are given. And what we are saying is, look, if the energy, so we are trying to say, is it, we are trying to narrow down the energy to being either below or above this inverse polynomial interval, right? We are trying to say, is the energy below this amount or larger than this amount? And these two are separated by an inverse polynomial. Now, what we are trying to do there is to say, okay, so we don't know how to solve this problem, but what we can do is we can map this problem into another one. So we can create a new Hamiltonian where if this ground energy used to be small, then the new one will be small. If this ground energy used to be slightly larger, inverse polynomial larger, then the new energy would be constant times m, where m is the total norm of the Hamiltonian. So now the gap becomes not constant like 0.1, but it becomes, the difference between, say, 0 and 0.2m.
And so this new Hamiltonian is not local Hamiltonian?
Which one?
Necessarily. If there were a quantum PCP theorem, it would not be local.
It might be local so one would expect it to be local in terms of a k local, meaning every term involves only k, some constant number of particles. But one would not expect it to be local in space, so like a 2-dimensional or 3-dimensional.
This is local in space.
This is also local in space. Yes.
I mean the area law.
Actually, so that's a very good question. So what Sanjeev asked is, for this area law to hold, do we need for it to be in 2-dimensional or 3-dimensional space? And the answer is, as far as we know, it might even hold for completely general graphs. So in other words, think of the terms of the Hamiltonian. So let's say it's too local in the sense that it's really a graph rather than a multigraph. But it would hold also for multigraphs. But let's say it's just graphs. And now let's say the interconnection pattern is completely arbitrary. Right? Then you could still define the surface area of a region. It's the number of edges that you cut. And as far as we know, the area law still holds that. And of course, but what happens there is if you're trying to prove the area law in an expander, it's of course very easy because in that case the surface area is proportional to the volume, and so you don't have anything to prove, right? So it could be that it scales, it's just completely arbitrary.
Although it's very unlikely, as we
It may be, yeah, there may be counterexamples, and so
And in any case, the area law doesn't imply a succinct representation.
that's right. That's right. So that's right. That's right. Yeah. So
Is it possible to do classical PCB theorem physical 2D?
I'm sorry.
Is it possible to do classical PCB theorem in 2D or 3D?
No. So the classical PCB theorem, about which, by the way, there's going to be Luca Torresan will speak on Friday. So no. So for that, you need some kind of expander graphs. So that was the point that Sanjeev was raising. That
So is it proven that in 2D or 3D it's PCB theorem?
yeah, because you could actually come up with some sort of approximation algorithm, to some extent. Right? Yeah.
Did you want to say something about, there's sort of these two, gap sort of refers to two different things. One is when you have a promise gap, and the other is where...
Yeah. No, I don't want to.
I want to, in response to the question of does an area law imply a succinct representation,
Yeah.
I guess my work with Fernando Brandao implies it does in a very weak sort of sense, and I'll mention that later on.
Great. Okay, so I should say that there's okay. So by the way, I realize I'm running into one of the things that I wanted to say about this workshop, which is that we will try to have have discussion trump schedule. Although I wasn't expecting to run into that particular issue in this lecture, and maybe I still won't. But in general, in this workshop, if you have questions, it's that's what it's meant for, and so you should really ask. And as speakers, you should I hope speakers will also be very comfortable about letting discussions continue. Okay, so in terms of the 1D in terms of the area law, there was this real breakthrough by Matt Hastings about 6 years ago, where he gave a rigorous proof of the 1D area law, the area law for 1D systems, where for 1D systems, what it says is if you cut the system at some point, then the entanglement entropy across this is proportional to the area. Well, what's the area here? It's just 1, so the entanglement entropy is a constant, and that's what he showed. And then there's been a lot of further work on this subject, and including not only getting much better parameters for this constant, but also this has been the subject where I guess from both sides, from physics and computer science, we've sort of beaten a path using machetes and till we met in the middle and can actually talk to each other and exchange techniques. In addition, there's also a polynomial time algorithm for approximating ground states of gapped 1D Hamiltonians. So this seems to go towards explaining somehow this result from condensed matter physics about DMRG, right? So now, yeah. I'm sorry?
Did you expect to get an exact algorithm in the 1D case?
An exact meaning just exactly the ground state? Yeah, so we
Up to numerical issue.
yeah, no, so the actual ground state could be extremely complex, right? So to describe it exactly, you might actually need the exponential amount of information, but what you can show is that they are, given, if you want to be arbitrarily close, then you get very good approximations where the issue is how much entanglement is there, across. So well, you can bound the entanglement entropy, but that doesn't mean, even though the entanglement entropy is bounded, it doesn't mean that they are on tiny terms which contribute very little to the entropy. But if you want the exact answer, you have to keep track of everything, and so you have to truncate somewhere, and then that contributes to your error. So you pick an error, a level of approximation, and then the area law kinds of results tell you that you can truncate somewhere, and then that's what leads to a given level of approximation.
And the running time depends on the error. And so
That's right. Yeah. So it depends. Yeah.
And I guess there are QMA completeness results that say you cannot improve on your.
That's right. So
in the 1D kit.
No, but there's no gap, no constant gap.
Right. So his algorithm depends on the gap and the error. If you say, can I have an algorithm that depends only very weakly on the gap and the error, like polylog dependence, then the answer is no because of these QMA completeness results.
Yeah, so it's about the gap case, 1D gap case.
Is that true even if you leave the gap?
No,
Fix
no,
the gap, right, and have the error go to 0, then can you exclude only log one word?
No, then we don't know.
That algorithm is only one word.
Yeah, that's right. Okay, so now I think the exciting part of it is not just the fact that we have these techniques that, at this point we really have a dialogue between physics and computer science on this. But not only that, we also have some very beautiful open questions, some far-reaching open questions. So some of these open questions have to do with how do you make a transition to 2 dimensions. So in terms of the area law, the results we have currently in rigorously proving area laws, they are right at the cusp of being able to prove something non-trivial about 2-dimensional systems. So, in fact, if you could make even a small improvement, a tiny improvement in the parameters of the 1D bound, you would get a non-trivial result for two dimensions. And so that's a very enticing open question, which is waiting to be worked on. The second very interesting question is algorithms for computing 2D ground states. So this is really the holy grail in condensed matter physics, to try to understand 2-dimensional systems. And there's a lot of recent work on trying to do classical simulations of 2D quantum systems, using this tensor network approach, various kinds of tensor networks, PEPs and mirrors and so on. But the new thing that's also been added to the mix is that now for one-dimensional systems we actually have some tools and rigorous techniques, and it should be very exciting to put all these together and see where this goes. So this is the other reason why this semester is so timely, because all these things are are happening there, and this is an opportunity to bring all the people together from different disciplines working on these problems and putting the ideas together. Okay, so let me spend the last.
One question.
Yeah.
So these empirically successful algorithms.
Yeah.
So 2 questions. One is, how do they know whether their simulation was successful? Do they have theorems that they verify whatever? And second, the systems that they're studying, are these synthetic systems, like randomly generated or what?
No.
Because
no.
there you might be able to prove.
No. In fact, okay. So these the successes are mainly in 1D, for 1D, so far, right? So 2D is really the frontier, and the successes here are relatively. This is sort of the beginnings of. So there's a lot of effort there, and for 2D systems, But I think it's fair to say that so far the most, 1D is considered sort of well solved and well understood, and 2D is really the frontier.
No, but how would you even know that you've done it right? I mean, what's the right answer?
Oh, I see. Yeah. So I think that the answer is physicists know.
Yeah.
I mean, if there's something exactly solved, you could do it on a system that you have an exact solution for using some complicated method.
Okay.
Like some special symmetry or something. And then if your algorithm doesn't take advantage of the symmetry and manage to get the right answer, then you feel pretty good about it.
I see.
So the other thing I should say about DMRG is that it doesn't always work. And in fact, often to make it work, what you have to do is you have to start with an initial configuration, an initial state, which you have to guess based on the physics. So if you just start off with any old configuration, it won't converge and it won't give you the right ground state. And so you have to have some physical insight which says, here's what the solution might look like, or here's some approximation or rough good starting point, and then you use the algorithm to find its way.
And then the second question was, on synthetic data, randomly chosen H's and so on.
I think
that's easier to prove theorems about.
Yeah, but I think it's my understanding is it works well in practice on interesting systems rather than on
synthetic.
On synthetic data. It may not work actually. So
I see.
Okay, so let me just say a little bit about untrusted quantum systems, untrusted quantum devices. So where you have a device, a quantum device, it's supposed to be doing something, and then you want to verify, does it really do what's claimed? As I said, one way you can model these untrusted devices is as black boxes, which are potentially exponentially powerful, certainly much more powerful than the classical tester who is trying to test these systems. And then you have limited access, say binary classical access. You want to. Okay, so now this is again a place where it touches on very fundamental constructs, because the place where we see computationally bounded verifiers trying to test something, talking to an untrusted, much more powerful system, is in interactive proofs in complexity theory. So what we should think of is a polynomial time classical verifier. This is the experimentalist or tester. And then we have a very powerful quantum system. But very powerful now is no longer infinitely powerful as it would be in interactive proof systems. Now the very powerful is quantum polynomial time. And so results from interactive proof systems like IP equal to P space no longer apply. And so the question is, what's the power? What can you convince Arthur about? What can Arthur sort of convince himself of in conversation with a quantum polynomial time Merlin? So there are very interesting results which I guess Anne will talk about today, which is so there are these papers which talk about what happens if you augment the verifier with a small amount of extra quantumness. So some constant number of qubits of quantum storage and a quantum channel to Merlin. But other than that, you have Arthur with this small augmentation. Other than that is classical and is interacting with Merlin. And so it turns out in this case you can actually verify anything that Merlin says. Now there's one other setting in which you can explore these questions, which is quantum multiplayer games. So in this setting, you have Arthur, who is polynomial time bounded, and then you think of Merlin as these quantum systems, but more than one quantum system, which are entangled with each other and which are not allowed to communicate with each other. So you put these quantum computers in 2 different rooms, and you make sure they can't talk to each other, but you make sure that they're also entangled with each other. Now, this kind of quantum multiplayer game in a very elementary form, go back to, the very early history of quantum mechanics with this EPR paradox, or spooky action at a distance, this initial understanding of entanglement. And then with this beautiful result of John Bell, the Bell's inequalities, which are these so-called tests for quantumness, which actually test that 2 systems must be quantum because a classical Arthur interacting with these 2 systems, or maybe Arthur now is split into 2 parts. One part is interacting with one system and the other with the other one. These are very far apart. They can't communicate with each other, the two quantum systems. And just the classical interaction with these systems is completely incompatible with any classical theory, right? So, and so what quantum mechanics predicts about the probability distributions on these interactions is completely incompatible with classical theories. So it turns out that you can use these kinds of tests for quantumness to do device-independent quantum cryptography, to certify random numbers, and to actually certify that these quantum systems behaved exactly as they were supposed to, according to protocol. So again, this is something that we'll hear about. I'll talk about also the general outline of the workshop. Finally, let me say that one can get arbitrarily philosophical with these questions. So you can take them to the limit by asking about how you could possibly test quantum mechanics. So here's one way you can think about it. So this exponential growth of the exponential complexity of quantum states. This is at least from where I sit, it's the most counterintuitive aspect of quantum mechanics. And then if you look at it from this viewpoint, that the thing that you want to do, the thing that physicists do always, is to test the limits. The theory in the limits of very high energy or very small scales or very large velocities. And each time you test physics in these limits, something interesting happens. And so you could ask, well, is something interesting going to happen when we test physics in the limit of high complexity? In the limit of large numbers of particles, well, not even that large, and see whether it really does exhibit this kind of exponential complexity. And well, when you think about this, you immediately realize that, in fact, there's a problem, because this high complexity which you want to test also precludes you from doing a test. Because if you were going to use the standard scientific method, what you would do is you would first, design an experiment, you'd sit down and calculate what the outcome should be, and then you'd go perform the experiment, hopefully, and then check to see whether the outcome was exactly what you predicted within experimental error. But then, the high complexity actually is a barrier to actually calculating what the outcome should be. So how would we as classical beings possibly carry out this method of testing quantum mechanics at this level? And so, well, this general outline that I talked about interactive proofs, if we could implement it in a completely unrestricted form. So far we have implementations where either you augment Arthur with some amount of quantum bits, or you rely on Merlin being 2 separate systems entangled, and you actually make use of properties of quantum mechanics. But let's say that we actually went back and solved this basic question. Is it the case that a polynomial time verifier interacting with a quantum polynomial time untrusted prover can verify everything about it? That quantum polynomial time is equal to quantum interactive proofs with quantum polynomial time provers. In that case, you would actually be able to verify quantum mechanics, because whatever experiment you wanted to verify, you would actually, instead of first calculating the outcome of that experiment, what you would do is you would have a more civilized interaction with your physical apparatus, where you'd sit down in the lab and you'd carry out a conversation going back and forth, with an interactive proof. And at the end of that interactive proof, you'd be convinced that in fact the apparatus was behaving according to whatever property you were testing, whatever theory you wanted to test.
Your slide a couple of slides ago, I thought you said that VQP was QPAP.
Oh, sorry, did I say that? I should have put a star there.
One back. Okay, two back.
Okay, so oops,
No.
one more. No,
Oh,
I
you
didn't.
said yes. You said yes if Arthur has.
Yeah. If Arthur has
What
a
was
constant.
the yes to?
Yeah. So that.
Oh, I see.
So when I say QPIP, I mean without this. So I think this would be called QPIP star, right? So if you have those extra quantum bits. Okay, so let me just summarize and wrap up. So, oops, sorry. Okay, so so just to summarize, what quantum Hamiltonian complexity investigates is implications of these two properties: the exponential description of quantum states and the limited access. What does this tell us about physics, about the physical world? Now, what makes this an interesting field is a number of coincidences. The first one being that the central questions of condensed matter physics and quantum complexity theory are, at some level of abstraction, they are the same question, right? That there's lots of recent work on these frontiers, so there's an emerging common language, and we really can talk to each other. But there are also a lot of very interesting questions, some of which we know and some of which we actually don't know. So each side really needs to talk to the other in order to actually formulate the best questions and how to put these techniques together. And so this should really be an exciting semester, and hopefully a party. And okay, and then there are all these exciting open questions, which are, well, I sort of highlighted the biggest ones, but then there are lots of other questions as well. I guess just before I finish, I'll take 2 minutes to walk you through the program for the workshop. So there are, I guess we have 3.5 days, and we have a broad theme for each day. So so today's talks are broadly on quantum multiplayer games and untrusted quantum devices. So Anne Broadbent will start us off with talking about how to delegated quantum computation, or how to test if a quantum computer is quantum. Yaryun will talk about untrusted quantum devices in greater generality. And then we'll follow up with a mini crash course by Thomas. So let me just say a little bit about the our ambition for these mini crash courses. So what we did was we singled out 5 different subjects which are very basic, and where which it would be good to understand these in some depth, and the charge to the speakers was to make these mini crash courses sort of to have them be not to start off with the absolute basics, but to sort of provide this kind of sophisticated basic picture that that you'd like to have about that subject if you needed to use it, but you don't really want to work in it. So so for example, if you were let's take the example of quantum information theory. Let's say you cannot avoid knowing something about quantum information theory, no matter what you work on in this subject. But let's say you are not really interested in quantum information theory. You don't want to read a paper on the subject. What is it that you should know so that you have a picture of it and you have a working knowledge of it, at the level that, because when somebody really knows the area, they keep drawing on a certain picture, simple picture, and a few simple facts, which, if only you knew, you could actually get through 75% of what they do. And so the hope is that that's what these courses will actually, these mini crash courses will actually convey. And so what Thomas will talk about is a mini crash course on quantum multiplayer games. Tomorrow we'll have the day will focus on area laws and quantum information theory, starting with Daniel Nagai and Zef Landau talking about area laws, and Ashwin will give us a mini crash course on quantum information theory. And then we'll have applications of quantum information theory in two different areas, in quantum Hamiltonian complexity by Aram Harrow, and to I guess quantum gravity by Patrick Hayden. On Friday, we'll focus mostly on the quantum PCP theorem. So with, again, a mini crash course on what you should know about the classical PCP theorem by Luca Trevisan. And Thomas Vedek recently co-wrote a survey paper on what we know about the quantum PCP theorem, and so he'll tell us a lot more about that. Aram Harrow will talk about STP hierarchies, and then there's another mini crash course on quantum error correction, which is very related to the quantum PCP theorem. And then the last day, on Saturday we'll have a half day it's unfortunate that this mini crash course on tensor networks comes so late, but it's really quite fundamental to understanding how to not just do quantum simulations, but also it's a very nice language in which to think about quantum states. And then we'll have talks about quantum simulation by Daniel Nagai and John Preskill. So just before ending, let me just say one more thing, that there was a reading group last semester that SEV organized with a number of people where they on quantum Hamiltonian complexity, where they've actually put together a document which I hope is going to be useful to many of you. It's a survey paper on quantum Hamiltonian complexity. It's been posted on the website of the program on if you go to simons.berkeley.edu, you'll find it there. So please take a look. Oh, sorry. Yeah. So it's on the bootcamp page. So you have to go all the way there, and it's posted there. Okay. Thank you. Thanks very much. Yeah.
There was a point you made in both the spring workshop and the main complex as to why it doesn't matter people focus on the ground state.
Why would they focus on the ground state? Well, actually, perhaps I should say the ground state is proxy for ground and low energy states. And I guess you would want to go back to this, so if you're at low temperature, then you're in, somewhere in that region. That's what.
Right, but if you're not at very low temperature and want to understand point correlations.
So
I mean, they have some reasoning for this.
Then you expect to be in a thermal state, which is some part of the ground state and some of the excited. You want to really understand what's going on there. Like, how will the system behave at different temperatures? Will it be superconducting? Will it be magnetized? And you need to know parts of the spec.
I think it's easier as temperature goes up usually.
Yeah.
Ground state's sort of the hardest.
Yeah. And when you're cooling down, can get stuck. You need to do annealing, whatever.
For example, area laws are known for temperatures away from zero.
In the classical case, there are known situations where the complexity of approximating what's happening, is easy for a while as temperature rises, and then gets hard, and then gets easy again. There's all kinds of phenomena, and I don't see that being expressed.
I guess maybe there's another way to talk about it. So one thing condensed matter physicists are very interested in these days is highly entangled states of matter or topological order, and then you really want to study sort of low temperature, right?
Yeah, no, for those systems, yes, but if you're interested in simulating physics, then
But this would be, maybe this is the kind of physics one wants to simulate?
maybe.
It's a related question. Do you know if ground state complexity tells you anything about dynamical complexity? So if you have a k-local Hamiltonian and you know the ground state complexity, can you get to this exponential Hilbert space starting from a particular initial state?
So let me try to at least say what I understood of the question and then answer it. So maybe you're saying, well, so let's say you found the ground state, but now you want to simulate the dynamics in the neighborhood of that ground state. Then how hard is that? And so if you look at some of these, the work of Vidal, for example, with mirrors, and so initially, he used the tensor networks to find the ground states, but then actually says you can actually use it to simulate dynamics in the neighborhood of the ground state, and it works actually extremely well. So I don't think there are any rigorous results there, but it seems to work well in practice. Okay, so shall we stop for a coffee break, and then we'll resume in 20 minutes?